given by Alfred Zong from the Gedi group, proving structural and electronic dynamics in fast budget or targeted wave.
All right, thanks for coming. My name is Alfred, and I'm from Gedik's group. And I'm going to continue the story of charge density wave from Yafang's talk. But this time, we are not looking with the axis of temperature or a magnetic field or anything, but we are looking with the axis of time. And as you can see already, we are trying to probe what happens to this charge density wave when we try to perturb it with the ultrafast laser pulse and watch how it evolves. So actually, let me begin with the story. So a little more than a year ago, I was in March meeting in Baltimore. Typically, there are so many talks to go to, right? You want to split yourself into 10 parts and go to 2 different talks. But this one pops up, reflection on the past, present, and future of condensed matter physics. And it's given by Tony Leggett, so this is the obvious choice. So I went to the talk, and it's pretty interesting. He talked about what were the paradigm shifts for the last 60 years or so. He mentioned Landau-Fermi liquid theory or BCS theory. He also talked about some other exciting developments that unfortunately didn't shift paradigms. You want to guess what are they? Good for it, superconductors and topological insulators. Well, I guess his answer may offend many people sitting here, but don't blame me, blame Tony. Then he went on to talk about what are the other condensed matter physics in the future. And this one pops up. Far-off equilibrium phenomena. And I was thinking, oh, that's exactly what I do every day. Now, when I think about it, what do we really want to observe in this far-off equilibrium phenomenon? I thought of 2 answers. The first one is the so-called creation of new state of matter. It sounds a little bit paradoxical because usually we define phases of matter under thermal equilibrium. So what do I really mean by new state of matter? Right, so maybe let's look at a classical analogy, which can give us some insight. So this is, probably many have seen this, is a Cabezas pendulum. So the idea is initially the inverted position is unstable, but when you drive the system with a periodic drive, then a new stable position emerges. Of course, this is a classical system, but the quantum analogy in this case is, for example, the Foucault block states in a topological insulator bismuth selenide. In this case, what we're doing is we're basically sending an ultra-fast laser pulse to this particular topological insulator, and we can see a coherent interaction of light and electrons to create this new states, so-called the Foucault block states. And here, what you're looking at is basically a direct cone of the surface states, measured from time-resolved TARPES. And as you send the laser pulse, you can see the replica bands spanning the energy space, and these are so-called the Foucault block states. Of course, we can also look at this same movie from a typical energy momentum cut. You can see replica of the direct cones, and then the direct cone disappears after the intense laser pulse goes away. So really says that this is only happening when the light pulse is incident on the sample. So, well, this is one example of what we can do with a non-equilibrium phenomenon. And for today, I'm not going to create new states. I'm going to study an existing state. But what we want to do is we want to study how phase transitions happening on an ultra-fast timescale. So again, when I say non-equilibrium phase transition, it may offend some theorists, probably, that phase transition should really be characterized with a thermal equilibrium condition. But here it really means is, for example, in the story of charge density wave, we want to send an ultra-fast laser here and see how it evolves in both electronic system and the lattice system. So Yafang already mentioned that what is a charge density wave? In this experimentalist cartoon picture, in many systems, there is a coupled degree of freedom between electrons and lattice. So here we see a charge modulation of electrons. And at the same time, because of strong coupling between electron phonons, there's also a displacement of the lattice ions into a lower symmetry position, or we call it a superlattice. So here we're basically sending a light and see how both the lattice and the electrons evolve over time. So here is a preview of what I'm going to talk about later. But without getting into too much experimental details, here's the first movie I want to show, where this is basically a measured ARPES spectrum. So on the right-hand side, you're seeing the Fermi surface map. of this particular charge density wave material, lanthanum tritelluride, which is a prototypical example of a one-dimensional charge density wave. You can't see much intensity here because, as Yafan said, when you go into the charge density wave state, much part of the Fermi surface gapped out. That's why you didn't see much intensity. Here I'm taking a specific cut to see the energy versus momentum dispersion relationship. And this is basically the band that's supposed to cross EF, but it actually doesn't cross the Fermi energy. And for this particular material, the energy gap is pretty huge. It's almost 400 MeV. So as we pump the system, we can see there's a partial suppression of the gap. And if we look at from the Fermi surface map, you can see a partial closure of the Fermi surface as well when the light incident on the sample. And basically, I'm going to go to more details to explain this movie later, but here's a kind of zeroth order observation. So the TARPES is measuring the electronic response. And of course, a second probe we can do is to look at how the lattice ion responds to this ultrafast laser pulse. So here we're looking at an electron diffraction pattern. So in normal crystal, we can see Bragg peaks, but when the system is in a CDW state, you can also see superlattice peaks due to the superlattice formation. So these two little dots indicated here are the superlattice peak. And as the pump arrives, you can see the suppression of the peak. And then soon after, the peak recovers. Again, this is just a preview of what I'm going to explain later. But basically, the idea is we want to watch the lattice movement and the electron movement together as we perturb the system. So here's the outline of the talk. I will do a little bit digression first to talk about the two techniques we used to produce the two movies you just saw. Time-resolved TARPES with the XUV beamline, as well as ultrafast electron diffraction. And then I'm going to explain more quantitatively what the observations are and try to reconstruct a picture of what exactly happened when we pump the system with a laser pulse. So here's the setup we used to produce the first movie, the time-resolved TARPES. Briefly speaking, we have an amplified laser system, and the laser pulse from the laser system is split into two paths. The first path is the so-called pump path, which is used to excite the sample, which is not really drawn here. The second path we call the probe path. The probe path is used to generate the XUV light source used to do the TARPES measurement. So we here first generate the XUV light, or XUV stands for extreme UV light, and then use the monochromator to select the specific energy we want to use. And then it passes through the diagnostic chamber, and then finally sent to the sample sitting in the center of this measuring chamber. Here you can see we have a pretty special type of detector, which is a time-of-flight detector. If you are familiar with TARPES, many groups actually use the so-called hemispherical detector. But here, we use the time-of-flight detector because we can really get the three-dimensional information about band dispersion at one time. So the three dimensions are basically the two in-plane momentum, the Ks and Ky, and then the energy axis, the vertical axis, which is calculated from basically the time it takes for the electron to travel from sample to the detector, and then it converts to the energy. And then we generate the XUV light by using inert gas in a hollow fiber. So there are two operation modes for our TARPES setup. The high harmonic mode, basically we send in a very intense ultra-short pulse of near-infrared light. And then by a high harmonic generation process, we can produce up to 30 eV at 30 kilohertz rep rate of lasers. Another mode of operation which is used in the current study I'm going to present is the night harmonic mode, where we send the third harmonic of a near-infrared laser first to this hollow fiber, and it generates the other third harmonic. So a third of the third harmonic is basically the ninth harmonic, which can give us up to 10.8 eV. I want to emphasize that here we can actually get down to below 20 MeV resolutions, which is very close to the Heisenberg limits, considering the time resolution is about 230 femtosecond. So we see that time-resolved TARPES can give us information about, for example, how does electronic band structure change. Of course, the other side of the coin is how does lattice change. And in this case, we use the so-called ultrafast electron diffraction. Essentially, it is electron diffraction, but we take a diffraction image at every instant of time after the pump pulse arrival on the sample. So basically, this is schematic diagrams where we generate the electron pulse by putting UV light to a photocathode where we generate electron bunch through the photoemission process. So there are several advantages of doing electron diffractions. I won't go through every one of them, but basically the idea is compared to its close counterpart of, say, X-ray diffractions. Electron diffraction have much higher cross sections, so you don't have to wait for like 10 hours to get the same amount of signals from non-resonant X-ray diffraction. For resonant X-ray diffraction, it's a different story. And of course, compared to, for example, X-ray diffraction, where you can also get this kind of structural information, UED is usually a much compact setup where you can actually build in a lab instead of, say, going to some beamline facility where you actually, for example, use a free electron laser to create an X-ray source to do time-resolved X-ray studies. Yeah, so with that little digression, let's actually go into the meat of today's talk about really what happens to the charge density wave as we pump the system with the ultrafast laser. I will begin by saying some brief words about the system we study. It's lanthanum tritelluride, but really it is an entire class of materials of rare earth tritelluride, where R stands for rare earth, the lanthanide series. So the entire series, you can see from the periodic table here that all of them exhibit a charge density wave transitions. Here, actually, I'm only plot part of the series here because for lighter atoms, here the transition temperature is rather high. In particular, for the specific case of lanthanum tritelluride we study, which is really the first atom in this series, the transition temperature is so high that it's probably above 600 Kelvin, pretty much close to the destruction limit of this sample itself. So as we cool down below the first transition temperature, one-dimensional charge density wave forms, and basically here is a cartoon picture to show there's something like a stripe order. For some of the atoms, of the rare earth atoms, especially heavier ones starting from dysprosium, as you cool down further, a second phase transition happens, which basically show an orthogonal direction to the first CDW. So you can loosely call it a checkerboard pattern. Here, I just want to briefly show the crystal structure. The material itself is also highly two-dimensional. It basically consists of two tellurium square lattices, which basically make up the Fermi surface, and which is sandwiched by the two tellurium rare earth slabs, which acts as a charged reservoir. If you are familiar with cuprates, basically you can make some analogies here where we have copper oxide planes, which give rise to the Fermi surface, sandwiched by the two charged reservoir layers from a variety of different cuprates. And also, they are both square-like. Here, I want to emphasize that even though it's almost a square, it's not exactly a square. So A and C, the two in-plane axes, differ by a tiny little bit. That's why when you cool down the sample, the charge density wave always have a preferred direction to form. That's why it's stripe order. It's not a spontaneous breaking of the A and C symmetry, but rather the lattice itself determines A and C are not the same to start with. As I said, the Fermi surface here is pretty much determined by the 5p orbital of the tellurium atoms inside these square lattices. And here is just showing a schematic from the first order tight binding calculations. And here I just want to label the wave vector that forms the charge density wave for the first transitions. And very similar to many other charge density wave, as experimentalists, you probably expect charge density wave is always not alone. And in fact, for this particular material, if you look at the phase diagram, if you either pressure it or you chemical doping it, some other phases, such as superconductivity, can also emerge. But today, we are not focusing on this complex phase diagram here, but rather we look at, for example, how charge density wave can get evolved with ultrafast light. Okay, yeah, so now let's go into the experimental results sections, where what we're really doing is we use three kind of different ultrafast probes, specifically ultrafast electron diffraction, transient reflectivity, where we measure basically how this reflectivity changes as a function of time after the pump pulse arrival. And then, as I explained, time-resolved ARPES. To first look at how the lattice dynamics evolve, and then look at how the electronic dynamics evolve. So again, this is a static electron diffraction patterns, where the big peaks are the Bragg peaks, and these little small peaks are the charge density wave superlattice peak. So you saw in the movie already that, for example, if you look at this charge density wave peak, it gets suppressed as we pump with the ultrafast laser. And if you just put that into a two-dimensional graph, here basically we're saying the integrated intensity of this peak decreases and then quickly bounce back. For this particular excitation fluence we use, the characteristic timescale of the decreasing is less than 1 picosecond, and it is below our time resolution in the instrument. And very quickly, or relatively quickly, it takes about 1.8 picoseconds to recover. Well, let's pause a little bit to really look at this diagram and see what's going on in the material. It's specifically what's going on in the material in terms of the lattice movement. So why does this decrease? Well, we know that from diffraction studies, the intensity of a diffraction superlattice peak is basically proportional to the square of the order parameter magnitude. Basically, a suppression of this intensity means that, for example, initially this is original charge density modulation and is suppressed. Yes, that can give us some suppression. We should also consider, for example, what happens to the phase of the charge density wave order parameter. And if you crank up the calculations, you will find out that the phase, basically phase modulation, which is cartoon picture depicted as kind of moving charge density wave sliding around, will give you a Debye-Water factor-like suppression, which is also exponential. So both of these factors contribute to the suppression of this intensity observed here. So pictorially, what happens is as you pump with the laser, in terms of lattice movement, the distortion gets suppressed, and at the same time, there's a lot of phase fluctuations. Well, we can dig deeper by looking at what exactly is the profile of the peak at, for example, this representative time point. So basically, I plot the raw data of this superlattice peak at this color bar positions. You can see basically it gets suppressed around 1.2 picoseconds, and then get basically enhanced again. If you look at the graph here, on the right-hand side, more carefully, you can also see there seems to be a broadening of the peak as you suppress its intensity. And we can, of course, also fit all the peaks as a function of time. And basically, this is the Fluence half maximum from the fitting plotted as a function of time, where we see basically two features. One is we already see that it got broadened. And second, the recovery of the peak width is in line with the recovery of the intensity itself. So what does broaden mean? Well, loosely speaking, broadening of the peak tells you there's a loss of long-range coherence. And from a cartoon picture point of view, for example, if this is the entire domain of CW order parameter before the pump excitation, a loss of long-range coherence basically means they're creating a lot of different small domains of fluctuating charge density wave as we pump and suppress the CW intensity here. Of course, this is not the best picture to represent here because it's really not a static domain was sitting there. They will be fluctuating all the time, but I try my best. So basically, the idea here is the suppression of the intensity is accompanied by basically the formation of these small puddles of this fluctuation of charge density wave. You can also look at this graph and see, oops, it doesn't really get suppressed all the way to 0. There's still some residual intensity remaining. So of course, as an experimentalist, you are thinking, can we actually suppress it fully? Yes, we can by just tuning up the laser power to pump it. If you're really hardcore about destroying the CW peak, you can also burn the sample. So this is what we did exactly. So we, So this is basically what we did. We tuned the pump laser excitation fluence. And we observed that at very low excitations, there's a very tiny suppression of the intensities. But if we pump harder and harder and harder, the CW peak basically gets essentially suppressed in terms of its intensity. And you can summarize this plot by sitting here at around 1.2 picoseconds and basically plot its intensity as a function of fluence, which is summarized in the plot on the right-hand side. Again, we see that around 8.5-ish observed fluence in terms of number of photons incident per centimeter square, we see almost a full destruction of the intensity of the CW peak, which is below our detection limit. So this is all good. It's all within expectation. You pump harder, you suppress the intensity more. And But we bear in mind this is all from the diffraction studies, which basically paint the picture of what happens to the ions, a lattice, during this ultrafast process. So now let's switch gear a little bit and see what happens to the electrons. Okay? So what's the simplest technique we can use? TARPES is, of course, a good technique, but the simple one is just to measure reflectivity. Basically, reflectivity reflects how the dielectric constants change as a function of time as you populate different bands and you excite quasi-particles to cross the c-level gap. So when we do that, this is what we get. So you are seeing here is basically, again, different curves correspond to different excitation fluence. We tune the pump power. And each trace represents the change of the reflectivity normalized to its normal reflectivity before the arrival of the pump pulse. So again, there are several features in this plot. So let's kind of dissect together. First of all, you can see there's small wiggles here, meaning there are some coherent oscillations being excited. And we can really see this in delta over R because you really give us a very good signal-to-noise ratio. You can look at here is like -3. So pictorically, that oscillation have basically many different frequency components. And the most prominent one is the 2.2 terahertz frequency. And if you look up the literature, that basically corresponds to the excitation of the amplitude mode. And in cartoon picture, basically this is kind of a amplitude of the charge density wave is breathing larger and smaller as a function of time. And since all of them are coherent, if we excite them at the same time, we can really observe this long-range coherence of the amplitude mode. That's why it shows up in these modulations in the delta R or R signal. And of course, we can also see how does this oscillations evolve as a function of fluence. Do we still see this oscillation at very high fluence? So here we do the plot. So basically, we normalize this amplitude of this amplitude mode. I know it's a lot awkward, amplitude of amplitude mode, normalized by basically the peak intensity, where peak intensity basically represents how much pump power, how much quasi-particle we excite from the system. And again, we show a similar critical behavior basically beyond a certain fluence because of the loss of coherence, for example, due to the suppression of the amplitude of the charge density wave as well as creation of all little phase incoherent domains, we no longer observe a very strong coherence peak from these modulations. But I also want to point out, despite the fact that it is pretty much saturated here, if we look really closely here at these modulations, even at the highest excitation fluence, you can still see some wiggles. And if you do the Fourier transform, basically you can still extract the tiny little remaining peak. So the idea here is the modulation from the amplitude mode is always there, despite how hard we pump. And if we actually fit this frequency as a function of fluence, no matter how hard we pump, how much energy we put into the system, the frequency doesn't change. That means the amplitude mode doesn't soften. So that is kind of a bizarre phenomenon. I'm going to come back later. And of course, if you compare these two graphs, another striking observation is, well, if we pump very hard in terms of ultrafast electron diffraction, the intensity of peak doesn't recover that fast anymore. So here what we do is we fit each curve with the phenomenological models that basically tell us how fast this recovers with, say, a single exponential recovery. But if you see from the electron diffraction, see from transient reflectivity measurements, it's really fast. And it's summarized in the plot on the right-hand side. Basically, the red dot represents the recovery time of the sea level peak, and the green dots represents the recovery of the transient reflectivity measurement. And there seems to be behaving very differently, especially at large fluence, where one is really fast, one recovers really slowly.
So is the reflectance measured at a particular wavelength, or what, is it just broad reflectance?
It's measured at a particular wavelength.
Okay.
Yeah.
How did you pick that, or does that matter?
It doesn't matter in terms of recovery time. It matters with, for different wavelengths you probe, you can see different proportion of kind of frequency coherent oscillations because it couples to different phonon modes with different Raman matrix elements. But in all, we actually do the white light broadband probe, and in all the wavelength probe, we see this very strong suppression signals. Yeah.
In
Yeah.
Is that permanent, or does that eventually recover?
That's pretty much permanent within our time window probe, and that's basically due to heating effect. As we pump a lot of power into the sample gets heated up by, say, 16 or even 5 picoseconds. And that's just a reflectance of the thermal change of the reflectivity.
It's not damaged?
It's not damaged, yeah. Well, it's not damaged because also this is not just one pulse, right? It's repeated pulse. Means the curve is reproduced every single pulse is arrived, so yeah. So why there's a difference in time scale? Well, the first idea that pops out in mind is basically, oops, okay, this is probing the lattice and this is probing the electrons. So basically there's maybe a decoupling of lattice and the electrons at this ultra-fast time scale. Ultimately, we're talking about so-called a non-equilibrium phase transition. I want you to keep that in mind while we move on to some further data to either prove this or disprove this. But this is maybe the first idea that pops out in mind. So, okay, everything's all good. But what about ARPES? Does ARPES agree with maybe the timescale seen in ultrafast electron diffraction, or does ARPES agree with the timescale seen in transient reflectivity? So here we go. This is the Fermi surface, and we are looking at the field of view in this blue circle. And this is basically the Fermi surface. I cheated here a little bit. I didn't put the Fermi surface at before time zero, basically before the pump arrived, because you can see nothing. As you see, it's pretty much gapped out. So here I put a Fermi surface map at 300 femtoseconds after the arrival of pump pulse, where you can see partial population of the Fermi surface. So if we take this particular cut again, where you see in the movie, and take some snapshots at different time delay, this is before time zero and after time zero, we can see how the band evolves. So let's look at this picture more carefully. So in the equilibrium state, basically you can see the backbending of the bands of this 5p tellurium PZ band that basically opens the gap delta roughly equals to 360 millieV due to the formation of charge density wave. And now what we do is we pump this state with ultrafast laser, and then just right after the arrival of the pump pulse, we see some population of states above the Fermi level. Basically, it's populating basically the 5p band above the Fermi level. And as time goes on, we can see that actually this population decrease in energy. So there represents basically a partial suppression of the gap. And of course, as time goes on, the relaxation of the quasi-particle will be back to this. And eventually, after a few picoseconds, it's just under a quasi-equilibrium where we have kind of a hotter CDW state. So how do we extract the time scale here? We can, of course, maybe look at this particular point where the gap is largest. And we can plot the integrated intensity within this momentum range as a function of time for different energies. So basically, this is a two-dimensional plot from this four-dimensional data, where we sit at this momentum, plot this energy versus the deleted time. Again, we can fit, for example, the band edge of the upper band that's being populated here. And again, we see kind of suppression of the band from the upper CD level band, and then a quick recovery. It's not really more reliable to fit after about a few hundred femtoseconds because of quick recovery or quick relaxation of the quasi-particle into the valence band. But we can still clearly see a trend here. And to estimate the time scale basically from ARPES data, for example, how does the gap closes and reopens, even though we couldn't fit the gap very accurately, we can use, for example, the spectral weight around EF as a proxy to measure how much spectral weight filled in the gap, and then how much this spectral weight relaxes back to its equilibrium positions. So basically, what we're doing here is we integrate all the spectral weights within these energy windows, and see, first of all, within a few hundred femtoseconds, there is a filling in of spectral weight, and that's basically representative of a partial closing of the gap. And then quickly, the gap reopens, which is represented by the relaxation of this spectral weight in the gapped region. And of course, we can also fit this with a single exponential decay and extract the time constant. And here's the result. We did two other fluences, and we combine the three ARPES points into our previous plot. So you have seen the red curve and green curve before, and basically the three white squares are the ARPES timescales, which agree pretty much well with the electronic relaxation time seen in delta R over R. Aha, so now you think, so ARPES and transient reflectivity shows the same timescale. So it must be electron and the phonon are decoupled during the recovery process, because ultimately in ultrafast electron diffraction, you are probing the lattice recovery, while in ARPES and in transient reflectivity, you are probing the electron recovery. But is it really the case? We thought about it for a long time, actually, but eventually come to the conclusion that this couldn't be the case. The reason is, here we're talking about a time scale of, say, 4 picoseconds or 5 picoseconds, and that is at least an order of magnitude longer than the typical electron-phonon interaction time. In fact, we can quantitatively estimate what is the scattering time between electron phonons by just looking at the delta over R plot and extract it to a zero fluence. Basically, that represents the intrinsic quasi-particle relaxation through, for example, the interaction of electron phonons. And that's happening around just a few hundred femtoseconds. And typically in most systems, particularly in this system as well, which is partially metallic, electron-phonon interaction is well below 1 picosecond. So it couldn't really be the case where up to 4 or 5 picoseconds, electrons still do not talk to the phonon and still recover really fast without restoring the lattice distortion. Then what could be the case to explain the dichotomy here seen in different ultrafast techniques here, if it's not a decoupling of electron and phonons? Well, let's kind of do a summary of what we have observed so far. So from UED, we observed there's a suppression of the intensities, and there's also broadening effect. And both are very slow in terms of recovery. And in transient reflectivity, what we see a suppression of the coherent oscillation of the amplitude mode. But bear in mind that amplitude mode doesn't really go away even if we pump really hard. And again, it also doesn't soften even beyond a critical fluence where the CW peak seen in UED is fully melted. And of course, in ARPES, we see, for example, there's a partial suppression energy gap. As you see from the previous plot, that the gap doesn't really fully close. And again, there's a very fast recovery in terms of the spectral weight inside the gap. So what could be the picture here? So eventually, to combine all these observations together, here is kind of what we thought really happens. So first of all, you have kind of a long-range order of charge density wave throughout the materials, for example, and which is represented by basically these red bars representing charge modulations. And this is a plot of cartoon picture of electrodensity modulations. Then you pump with the ultrafast light. What happens first is basically, as we see, there's a broadening effect of the UED peak. It creates a lot of small domains. And of course, concomitantly, there is a suppression in amplitude, and which is represented by a lighter color of these charge density modulations. And also, again, we discussed about the phase fluctuations, which is represented by this horizontal phase fluctuations, again with amplitude fluctuations represented by these vertical arrows. So how does this explain the observation here? So first of all, we know due to the suppression of amplitude and the suppression of the and the excitation of the phase mode, there's a suppression of the CW peak intensity. And of course, the formation of the small domains will explain there's actually a broadening effect of the loss of long-range order. And beyond the critical fluence, basically this huge fluctuation of the phase, the suppression of intensity, as well as the formation of domain will basically drive the intensity of the CW peak below our detection limit. That's why it seems that it basically vanishes. And on the other hand, the suppression of a coherent amplitude mode can be explained by the fact that basically in these small puddles of this charge density wave, there's loss of the long-range coherence. That's why you do not detect the coherent oscillation in the delta over R signals. I'll come to the fact that it doesn't soften and the amplitude mode remains later. But it also explains basically there's transient suppression of the gap, where basically there's still a suppression amplitude of the order parameter, which is essentially being probed by the gap size of ARPES. And what happened next? Well, something must recover fast. And we think that the something is the amplitude of the order parameter. So basically, it's seen by, again, this charge density modulation and the intensity of this color of the bars. We think that within 400 femtoseconds to a few picoseconds, basically depending on fluence you probe, there's a very fast recovery of the amplitude of the order parameter. And basically, this explains why there's a, fast recovery of the gap, where ARPES measurements basically measures the amplitude of the order parameter. And because of the fast recovery of gap, there's also fast recovery of delta R over R, because basically what you measure in terms of timescale of delta R over R, besides the electron-phonon coupling due to the relaxation of quasiparticles, is basically the relaxation of quasiparticle across the gap. And the gap recovers, it's natural to basically expect that delta R over R signals also recovers pretty fast. And then what happens slowly is basically the destruction of the domain walls and also the recovery of the phase mode. And basically, that explains why there's a slow recovery of the CDW peak intensity. And this happens at the same time scale as the narrowing back of the CDW peak. So to conclude the talk, basically, we have seen an example of using different ultrafast techniques to probe basically what happens in a non-equilibrium phase transitions. I actually put a quote-unquote concerted effort here because sometimes if you use more techniques, you may not produce more papers because they're all kind of inconsistent from the first look. But the hope here is if you use more techniques, you can produce more number of correct papers. And hopefully that's the case here. While the real conclusion here is basically in this particular system of the charge density suppression and recovery, we see there's a distinct time scales that stems from the amplitude recovery as well as the, which is distinct from the recovery of the topological defect and the phase coherence from this material. And kind of one message here is a different time scale seen in different techniques is not necessarily due to decoupling of the SAS systems, in this case electron phonons, seen in this kind of correlated material systems. And with that, I want to thank basically my colleagues in my group, and Yak Cheng from Pablo's group, Joshua from Ian Fisher's group, who provide the samples, and Boris, which basically provides the theory support. And yeah, thank you for your attention.
Yeah. So why should the amplitude recover faster than the domain size or the phase?
Yeah, so one idea that we have is basically for the domain to get annihilated, to some extent it's a topological defects where it takes a lot of energy to annihilate a domain where you have to have the domain wall propagate and two domain wall merges. Then you have a annihilation of domain walls, which is more energetically costly to recover. And also for the phase mode, for example, if you compare, say, phase fluctuation as compared to amplitude fluctuation, the phase mode in this incommensurate charge density wave materials, the phase mode is gapless, where we can easily populate low energy lying phase states. Where for amplitude mode, it is actually a gap. So in terms of energy costs, it's easily exciting the phase fluctuations as compared to the amplitude fluctuations. That's one idea we have.
Should the domain wall propagation annihilation be affected by temperature? Like the rate at which they move around and merge?
Yes, you should depend on temperature.
Have you checked whether that's temperature dependent?
Not yet. All the experiments done at room temperature. Yeah.
These experiments are all done at room temperature?
Yeah. All except for ARPES, the data is taken at the lowest temperature. But we did check the time scale of recovery at room temperature, and the cryogenic temperature is pretty much the same. Given that the TC of this material is more than 600 Kelvin, room temperature, in terms of phenomenology, room temperature and say 10 Kelvin is pretty much the same. And it's pretty much a second order phase transition.
Can you say something about the size of the domains? And also, if it's longer time scale, is it possible that it's a power law and not an exponential?
That's a good question. So for size of domain, we can basically estimate from the width of the CDW peak. But there's one problem here is basically then we need to characterize, for example, the instrument resolution, which we estimated that for this particular, basically for this particular width of the peak, we estimated is a few unit cells in terms of the domain size. And as for the power law, so there is some theory, for example, saying that power law recovery of the domain annihilation. I don't think from our short time probe we can differentiate the power law from exponential fit. Yeah, there are studies for other CDI materials which look at, for example, nanosecond recovery, which they do fit with, for example, a square root of time power law recovery. Yeah.
Are there any other questions?
Can you say again, why do you think that the electron Chladni's rate and lattice Chladni's rate are not decoupled?
Yeah, so basically, let's see. So there are really there are two regimes here. One is the regime of destruction of the charge density wave. In that regime, it can be decoupled in the sense that it's very easy to excite electronic quasiparticle really fast within maybe a few femtoseconds, 10 femtoseconds, and lattice hasn't had the time to respond. So typically, a lattice needs at least a quarter cycle of its amplitude mode, which is around 100 plus femtosecond to respond to that recovery. But here we're talking about the time scale of several picoseconds, which is way above the scattering time scale between electron phonons. So it's very hard to imagine that the electron still doesn't talk to phonons at that time.
Okay, are there any other questions? If not, let's thank Alfred again.